Hey everybody, Nick Russo here. Welcome to Cisco Live US 2020. In this session, we're going to discuss how to deploy and operate OSPF in modern networks, and I've developed a small business scenario that we're going to follow throughout the discussion. I've put my Twitter handle on the title page. It's at NickRusso42518. That's a great place to ask me questions as you go through the content. I'm usually pretty responsive, and I'm happy to help you if you get stuck somewhere or maybe you're not quite understanding some of the concepts we talk about. There's 5 main sections or modules in the discussion. We'll begin by talking about area design, and I'll illustrate some challenges that arise if you do it incorrectly or don't pay enough attention. We'll also discuss how OSPF can interact with BGP at the internet edge in a typical enterprise. There's a lot of ways to do this, but I have a few opinions here that I think will be helpful when it comes to doing things like load balancing, HA, traffic engineering, etc. I've also devised a method for scalably deploying OSPF over hub-spoke networks like DMVPN. I even wrote a free public white paper on this, which I'll link later in the discussion, but I think you'll enjoy this a lot, especially if you're forced to use OSPF in that environment. I also have a lot of experience designing extranets to connect to different enterprise partners, and oftentimes we use BGP or static routing for this, but OSPF can be a good choice too, assuming you design it correctly. After that, we'll discuss optimizing OSPF in a service provider environment. There are a lot of knobs here, but I just picked a few that we can look at so you have a better idea about the things that are important in carrier networks. I'll wrap up with a short conclusion that links some additional resources and recaps the high points from the technical discussion. In every training session I give, I like to set expectations around what I'm going to do and what I'm not going to do. I'm big into doing relatable scenarios, things that viewers can appreciate and relate to in their own networking experience. My goal is also to expand your thinking. I don't believe in just telling you basics about OSPF that you can find in any book on the market. The scenarios we'll look at, even though they are realistic and these all happen to me in real life with some modifications, they're going to seem a little bit different and a little bit weird. That's a good thing. This is a design and deployment discussion, not a hardcore config session. That being said, we're going to do a lot of design and a lot of detailed analysis with a little bit of config and validation on the command line. I feel like this is a good balance for a 2000 level session, which is intermediate level difficulty. I also like to be explicit about what I'm not going to cover in this session. I don't believe in just reciting facts. You can easily search that information on the internet and read about it. It's not worth anyone's time for me just to talk about this is how this works, and this is how that works, and this is how this works. That's why I like to build in the scenarios and the demos. It's way more fun. There's an infinite number of design choices you can make with any protocol, and I'm only going to evaluate a relatively small subset. I can't reasonably cover every single enumeration of every feature in every business environment, so I'm not even going to try. I also don't believe in stump the chump trivia questions. I'm not going to be teaching you about individual bits and flags and codes and low-level details that are important to understand for OSPF mastery, but contribute little when you're talking about design and deployment. So we're going to focus on practical outcomes, not technical mastery in this course. If you download the slides, you're going to notice a paper icon in the top right corner on some of the slides. Those slides are usually just fallbacks in case the demo fails during the live presentation, but that's an impossible case for recorded video training. Before we start, here's a list of the skills you should have before continuing. I consider this to be an intermediate level of OSPF knowledge. Again, you should understand things like LSAs and network types. You should have a basic idea of how the area types work. You should understand the OSPF path selection process, basic prefix summarization and filtering, and also a little bit about redistribution. You don't need to be an expert in any of these topics, and you really don't need a lot of configuration knowledge, but you do need a basic understanding of how these work and the problems they solve. You should also have a very basic understanding of how technologies like DMVPN, NAT, and EIGRP work, because we're going to use those in our networks to some extent. Last, you should have at least familiarity with IPv6. You don't need to be an expert, you don't even need production experience, but it shouldn't be completely new. Assuming you have basic skills in these areas, we can get started. When I give this session in a live talk, everyone gets a copy of my topology in a paper form on their desk in front of them. This is useful because they can take notes on it, they can reference it quickly while I go through my demos, and it's overall really useful. In a digital format, if you have a second monitor, I'd recommend just bringing this up and leaving it there as we move through the class because that'll make it easier for you to follow along. You can download the slides or just take a screenshot right now and hold on to that image as we move through. Okay, so all the intro stuff is done now. Let's take a quick look at our business scenario, then we'll move on to the technical content. So we've been hired by a fictitious company named Smart Building Central, or SBC. Their main product is a smart lighting system that they can sell to commercial and industrial customers. In the beginning, they only do the design work, so it's a bunch of white-collar engineer type people and they don't do any manufacturing or retail and distribution. However, they're trying to grow into those spaces, so obviously their network is going to need to grow, and it's going to need to grow in different ways in order to support these additional business activities. This is the essence of what we're going to be doing throughout the entire session. Probably the most fundamental deployment decision you'll make with OSPF is how to design your areas, so let's explore that first. Each of these technical explorations begins with a challenge, and in this case we're going to be dealing with a campus access network. Let's first assume that the SBC employees are having slow network experience and you need to figure out what's going on. Their Tier 1 operators notified you that there's some high CPU utilization throughout the network within OSPF, so we'll need to resolve that. And as it stands today, there are hundreds of old devices in Area 0. I'll be including snippets of the diagram on the right just to provide some context. So in this case, we're looking at just a small section of the network where R6 and R7 are like Internet Edge devices, R1 and R2 are like core distribution devices, and R3 and R4 are like access devices. Our customer has some constraints and some requirements around how our solution must look and must behave. We need to have some kind of scalable approach that's standards-based, so we can't introduce any Cisco proprietary technology to solve this. We also need to provide optimal routing to and from the internet. Now, it's worth noting that the red serial links in the diagram are the slower links, so when you see those are links we generally want to avoid and use for backup only. The solution also has to tolerate an access switch uplink failure, which means if the link fails between R1 and R3, we still need optimal routing to and from the internet. We'll examine 4 different cases here. We'll set the link between R1 and R2 in Area 0 and then look at the upstream and downstream flows. Then we'll put the link in Area 1 and reevaluate how the traffic flows. In this case, we'll start off with Area 0, and we can see the flow looks okay. R3 only has one upstream peer, which is R2, so the upstream traffic must flow that way. You might have noticed the C equals 5 on the diagram. That just means OSPF cost. On the reference topology, I mentioned that all the black links are cost of 10 by default, so this cost of 5 is less. That means that R2's shortest path to R6 goes through R1 as opposed to R7. The cost there would be 5 plus 10, which is 15, versus the cost through R7, which would be 10 plus 10, or 20. Once the traffic reaches R1, R1 must choose R6 because it's the only upstream path, and then of course R6 will have its shortest path to the internet through R19. For the purposes of this scenario, it's fair to assume that R6 is going to prefer its direct uplink to the internet, so don't worry too much about the Internet Edge BGP details in this session. Let's head to the command line for a quick demo to confirm this is the path using our show commands and traceroute. We'll use traceroute to the 192.0.2.19 IP address, which is hosted on the internet from R3. The upstream traffic from R3 takes the path of R2 to R1 to R6 out to the internet on R19. Let's quickly check the OSPF routes that we have that make this possible. As a quick side note, R3 doesn't have an exact route for this prefix because the ASBRs at the internet edge are originating default routes. We'll cover that more in the next module, but for now, we have a default that we can trace further. We can see that this is an external route, which was originated by R6 as the ASBR, and the next hop is R2. Let's go to R2 next to continue the manual trace. R2 should also have the default route. It was derived from the same external LSA, except this time, the next hop is R1. Let's check the default route once more. This time, the next hop is R6. R6 originates the default, so it doesn't make sense to check the routing table for it, but instead, let's check the fib to see how it gets to the final destination. It has a specific /24 route from R19. This was learned using external BGP or eBGP, and we're not going to talk too much about how BGP works, but just understand that this is a common mechanism that the internet can distribute routes down to customers. Long story short, this upstream flow looks pretty good to me. When we use Area 0 between R1 and R2, our upstream traffic works correctly, which is a good thing. However, the downstream traffic is another story. If we assume that R19 always picks R6 for its downstream flows, then the traffic takes a weird loop. Area 0 has two paths into Area 1, through R1 and R2, both of which are Area Border Routers or ABRs. When it comes to inter-area routing, you have to do two things. First, you have to determine what is the seed metric, or what is the LSA3, the summary LSA, what metric is that reporting from Area 1 into Area 0. These LSAs are generated by the ABRs and are going to specify what that cost is from the perspective of each ABR. If we look at Area 1, R1 has to take 3 hops to get there. So R1 to R4, R4 to R2, R2 to R3, that would be a cost of 30. However, R2 is directly connected, so that would just be a cost of 10. But in order to find the actual path, we need to also compute what is R6's path within Area 0 to get to each ABR. To get to R1, it's a cost of 10 because they're directly connected, and to get to R2, it's a cost of 15 because it would go R6 to R1, R1 to R2. The reason R6 doesn't go through R7 is because that cost is 20, which means it's greater. Now we need to take the sum of each pair of numbers. So 10 plus 15 is 25, and that's the cost using R2, and 10 plus 30 is 40, which is the cost through R1. That means that R6 is going to prefer R2, which is actually what we want. When we go into the demo, these numbers are actually going to say 26 and 41 because the loopback itself has cost, but that's really not relevant. I'm just trying to show the path information first. Even though OSPF computed the right path, we still have suboptimal routing according to the diagram. So why is that? The problem is that R1 is in the transit path towards R2. When R1 gets the packet, it's going to do its own autonomous independent lookup and forward the traffic the best way it knows. In R1's routing table, it's going to have an intra-area route inside Area 1 to get to R3. It's not smart enough to use the transit link between R1 and R2 because that is an inter-area route learned from R2's Type 3 LSA. Looking at a diagram, I realize this is kind of confusing, so let's go into a short demo so I can explain it in a little more detail. Let's also test the downstream flow from R6 down to R3 using traceroute. Looking at the diagram, we can see that this is a highly undesirable path. Let's check R6's specific route to R3's loopback to understand why. This is an inter-area route, which was derived from an LSA Type 3 originated by R2. That makes sense so far, and R6 is sending the traffic towards R1. Let's see how R1 gets to R3's loopback. This is an intra-area route, which was derived from R3's Type 1 LSA, the router LSA, and is accessible inside of Area 1. That's why R1 has to use R4 as the next hop, and it can't send traffic laterally to R2, which is definitely the better path. This is the interception I was talking about earlier. Let's go down to R4 to see what the rest of the path looks like. Not surprisingly, R4 sends the traffic back up to R2. Finally, R2 delivers it directly to R3. The problem with this is that R4 should not have been included in the transit path, and it's probably a small access switch, not the kind of thing you want a ton of traffic transiting across. Clearly, using Area 0 between R1 and R2 does not meet our design constraints. So we've ruled out using Area 0 between R1 and R2 because we've identified a suboptimal routing condition and that violates our constraints. Let's use Area 1 instead and see how well that works. Again, let's assume R6 is the preferred default route out to the internet. If the link between R1 and R3 is still down, R3 is going to choose R2, just like usual, because that's the only upstream path. Now, if we look at area 0, R2 only has one upstream option, which is R7. It can't laterally send upstream traffic to R1 anymore, even though the cost is less because that link is in area 1 when it needs to be in area 0. This is similar to the previous issue because OSPF is always going to prefer intra-area external routes over inter-area external routes. I like to use the word interception on these routers because it kind of indicates what's happening. You think your traffic is going a certain way, but then an intermediate router takes hold of it, does a routing lookup, and the traffic goes a different way. We can also assume that R7 chooses its direct link up to R19. Again, we're just using a basic eBGP here, and there's no BGP policy to make it work otherwise. Now, I'm aware you could use BGP to solve these problems, but again, we're going to look at how can we use OSPF in a simple way to overcome them. Let's do a demo to prove that this problem actually exists when we use area 1 between R1 and R2. Let's first test the upstream flow from R3 out to the internet using the same traceroute command we've been trying. Even though this path is fewer hops, it's actually much worse. R7 is sending traffic straight to R19 over the slow serial link when we generally want it to send traffic laterally to R6 to use our faster uplink. Let's check the default route on R3 to see what happened. As expected, we have our external route originated by R6, and our next hop is R2, so that's correct so far. Let's go to R2 next. Ideally, R2 should have a default route through R1, but that might not be possible this time. Because R1 and R2 don't have area 0 connectivity between each other, they can't exchange this prefix. R2 has to choose the intra-area external route over the inter-area one. This ensures that area 0 is chosen as the preferred transport area when reaching external prefixes. Next, we can check R7. R7 is also originating a default just like R6, so it learned a specific /24 from the carrier. This is another example of one of those interceptions where we think the traffic is going towards R6 because that was the LSA Type 5 that was preferred, but R7 got a hold of the packet and sent it the way it wanted. This becomes complicated when you have dense OSPF topologies and you need to decide what area to put the link in. Clearly, when using Area 1, the upstream traffic is not optimal. So we already know that using Area 1 isn't going to be sufficient to meet all our constraints, but let's at least explore the downstream flow. According to the diagram, this looks better at a glance. R19 always picks R6, assuming that BGP is working correctly and that our ingress is going to use the fastest link, so that's good. R6 still has two choices on how to enter Area 1. This time, the R1 seed metric is 15, which is 5 plus 10, which is better than the 30 we had before. The seed cost from R2 remains 10 because there's a direct connection from R2 to R3. There's also a difference inside Area 0. R6 is directly connected to R1, so its path cost to that ABR is 10, but to get to R2, R6 has to go through R7, which has a cost of 20. In this case, when we perform the math, we see that R1 is slightly better than R2. Suddenly, our downstream problem is fixed just by changing the area membership on one link in the network. R1 is the true shortest path, so this is the correct flow. There's no more interception because R1 can forward the traffic to R2 and then send it down to R3 without any crazy loops. Let's prove that this works using a quick demo on the command line. Let's verify the Area 1 downstream path by tracing to R3's loopback from R6. At a glance, this looks better, as R6 begins by sending traffic to R1. This time, the LSA Type 3 from R1 is preferred, so we may get a better ingress into Area 1. Let's go to R1 to check that. R1 is still going to have an intra-area route to R3, but it should take a different path. Because there's an Area 1 connection between R1 and R2, R1 is able to use the crosslink to send traffic to R2, which is a better path than looping through R4. Finally, we come to R2, which is the last hop in the chain. The only way to reach R3 right now is through R2, so this route doesn't change. Overall, using Area 1 makes the downstream path work correctly. So you're probably wondering, how can we fix this problem in a way that satisfies all the constraints? One solution is to use what I call link multiplexing. If you have a layer 2 technology that supports multiple virtual connections like Ethernet VLANs, frame relay DLCIs, etc., you could use that approach. In our example, we could create 2 different VLANs like VLAN 10 and 20, put one in each different area, run OSPF on it, and everything's going to work. The drawback is that it's configuration intensive. You need new interfaces, new IPs, new VLANs on any intermediate switches between the devices. It can be kind of a hassle. Another solution is to use GRE tunnels. So maybe you have a PPP link or something that can't be multiplexed. You can just use GRE tunnels with different tunnel keys. Inside the tunnels, just run different OSPF areas. It's really similar to the previous example, except now you're adding additional encapsulation. You still have new interfaces. And if you have any firewalls in between, you might have some security issues with inspection. A more interesting solution is to use an OSPF virtual link. This would run over Area 1, but the link itself is in Area 0, so you'd kind of get the best of both worlds here. It's tricky to understand and probably confusing for most operators, and it also scales poorly because you can only do a virtual link over one area at a time. Here's a quick comparison of the 5 different approaches we've discussed so far. We could put the link only in Area 0, only in Area 1, we can use VLANs, GRE tunnels, or virtual links. None of these solutions has a yes in every column. This should be an indication that none of these solutions are really appropriate for our business scenario. In this case, I would suggest using a relatively new OSPF feature named multi-area adjacency. This allows you to take a certain link, put it in multiple OSPF areas at a time by just adding more areas to it. For those familiar with IS to IS, it's similar to having an L1, L2 link between 2 routers and getting the best of both worlds by having both topologies over one common link. If we think about our problems, our upstream traffic is solved because R2 and R1 can send traffic freely between each other without needing to worry about OSPF path selection area boundary issues. I've also included a little config snippet for reference, but we're going to check this out on the command line next. At this point, I've quickly implemented the multi-area design, putting the link in Area 0 and adding Area 1 as a multi-area on top. You can see I have 2 neighbors with R2 because there's 2 rows with the same neighbor ID. One of those neighbors is over Ethernet 00, which is the basic Area 0 connection, and then I also have this virtual interface called OSPF MA1. This is just another virtual interface, kind of like a virtual link, and it represents our connection to R2 on Area 1. I'm also showing the configuration for reference, and you can see that this feature is supported both for OSPF v2 using IPv4 and OSPF v3 using IPv6. It's a simple configuration, and I should mention that the entire topology has IPv6 support everywhere. I'd encourage you to explore that later to improve your knowledge of OSPF v3 based on the skills I'm teaching you in this session. Let's go to R3 to test the upstream flow first. We'll use traceroute to the 192.0.2.19 address as we've always done. As expected, we have the optimal behavior, which was true when the crosslink was in Area 0. This allows the upstream traffic to flow the way we expect. Notice that we're taking R6 out to the internet over the fast uplink as opposed to R7, which is our backup. Let's check the downstream flow from R6's perspective to ensure that we don't loop through R4 anymore. We'll traceroute to R3's loopback to confirm it. This time we take the correct path by only using the ABRs and not looping through any Area 1 devices. We're not going to manually trace these paths as we did before because it's really just the best of both worlds. For the upstream flow, we can rely on the Area 0 connection, and for the downstream flow, we can rely on the Area 1 connection. That wraps up the first module. Coming up next, we're going to talk about how we can design our internet edge a little bit better based on our business goals.